Okay, so you want to build a semiconductor factory. Pour some concrete, buy a few machines, start stamping out chips, right? Here's the thing that's not even close to what's actually happening. A modern chip fab is, without exaggeration, the most expensive building humans have ever constructed for the purpose of making a single product. We're talking $20 billion, sometimes $40 billion, for one factory. TSMC's newest facility in Arizona alone is projected to cost around $65 billion once all phases are done. That's more than the GDP of entire countries. And by the end of this video, you'll understand exactly where that money goes, why the economics of chip making are almost impossibly brutal, why entire nations are throwing subsidies at this industry like it's a matter of survival, because honestly, it kind of is, and why, despite margins that sound insane on paper, most companies that try this still lose. Let's start with the basic anatomy of a fab, because there are really 3 tiers here, and they're 3 completely different businesses. At the bottom, you've got legacy fabs, older facilities making chips on mature nodes, the stuff that goes into your car, your washing machine, your thermostat. Building one of those runs you somewhere around $1 to $3 billion. Not cheap, but almost quaint compared to what's coming. In the middle, you've got mainstream logic fabs, making chips a few generations behind the cutting edge. Those run $10 to $15 billion. And then at the top, you've got the leading edge fabs, the ones making the chips that power your iPhone, your NVIDIA GPU, the AI models everyone's obsessed with right now. Those start around $20 billion and climb from there. And look, here's the part that should stop you in your tracks. About 70 to 80% of that cost isn't the building, it's not the land, it's the equipment. One single lithography machine, the kind made by a Dutch company called ASML, the only company on Earth that makes the most advanced version of this machine, costs around $380 million per machine. And a leading-edge fab needs dozens of these tools working in sequence, like an assembly line where every single station costs more than most people's houses combined, times 1,000. So why does it cost this much? Think of a chip fab like trying to build the world's most precise Swiss watch, except the watch has billions of moving parts, each one smaller than a virus, and you have to assemble the entire thing in a room so clean that a single dust particle floating through the air could destroy the product. That's not a metaphor for effect. That's literally what a clean room is. These facilities filter the air thousands of times per hour to keep it thousands of times cleaner than a hospital operating room. Workers wear what the industry actually calls bunny suits, full-body coverings, because a flake of human skin is, on this scale, roughly the size of a boulder landing on a circuit. The precision required is almost incomprehensible. Modern chips are printed with features around 3 nanometers wide. For context, a human hair is about 90,000 nanometers thick. You are essentially trying to draw a detailed street map of an entire city, except the map has to fit on a grain of rice, and it has to be perfect every single time at a rate of thousands of chips per hour. Now, here's where the money starts to flow back in, because once you understand the cost side, the revenue side is where this gets genuinely fascinating. A single 300mm wafer, that's the round silicon disk chips get carved out of, can be cut into hundreds of individual chips, and depending on what those chips are, that one wafer might sell for anywhere from a few $1,000s to, for the most advanced AI chips, over $20,000. Multiply that by the tens of thousands of wafers a single fab processes every month, and you start to see how a $20 billion building can actually pay for itself. TSMC, the largest contract chip maker in the world, pulls in gross margins north of 50%. Some product lines run even higher. That sounds absurd for a manufacturing business. Most manufacturers are thrilled with 15 or 20%. But chip making isn't really manufacturing in the traditional sense. It's manufacturing plus physics, plus about 2 decades of accumulated, nearly unreplicable know-how. That know-how is the actual product. The silicon is almost incidental. But here's the catch, and this is the part that quietly bankrupts companies that don't respect it. A fab is a depreciating, obsolescing asset from the moment it opens. Semiconductor manufacturing follows something close to Moore's law, this idea that computing power roughly doubles every couple of years. Which means the equipment you just spent $20 billion installing needs to be upgraded or replaced within a handful of years, or your fab starts making yesterday's chips at today's cost structure. Imagine buying a fleet of race cars for $20 billion, and then finding out every competitor's car gets 30% faster every 18 months, whether you upgrade or not. You either keep pouring money in, or you fall behind. And in this industry, falling behind isn't a minor setback. It's often fatal. That's why you'll hear engineers and executives in this space talk about something called Rock's Law, sort of the evil twin of Moore's Law, which observes that the cost of building a fab roughly doubles every 4 years. The chips get cheaper. The buildings that make them get dramatically more expensive. That gap is the entire tension of this industry. And this is exactly why fabs need to run essentially non-stop, 24 hours a day, 365 days a year, at extremely high utilization, just to make the math work. Every hour, a $20 billion facility sits idle as money evaporating. So companies chase what's called capacity utilization obsessively. You'll often hear the target thrown around as somewhere north of 80 or 90% utilization just to hit profitability, because the fixed costs are so enormous that the difference between a good year and a bad year often comes down to whether the fab was running at 70% capacity or 95%. Then there's the talent problem, which honestly might be scarier than the money problem. You can build a building. You can eventually buy the machines. But you cannot buy, overnight, the tens of thousands of specialized engineers who actually know how to run this equipment at atomic scale precision. Intel, TSMC, and Samsung have been refining this expertise for decades. When the US tried to jumpstart domestic chip production through the CHIPS Act, nearly $53 billion in subsidies. One of the biggest bottlenecks wasn't concrete or machinery. It was people. There simply aren't enough semiconductor engineers to staff these new megafabs, and training them takes years, not months. So why do companies still do this, knowing the risk? Because the alternative is worse. Whoever controls the most advanced chips controls AI, controls defense technology, controls basically the next century of computing. This has stopped being purely a business decision and become a geopolitical one, which is why governments in the US, Japan, South Korea, and the EU are subsidizing this industry. The way you'd subsidize something you consider a national security asset, not a normal factory. So here's the honest takeaway. A semiconductor fab is one of the highest margin, highest reward manufacturing businesses that has ever existed, and simultaneously, one of the fastest ways to torch tens of billions of dollars if you get the timing, the technology, or the talent wrong. It's not really a factory in the traditional sense. It's closer to a $20 billion bet, renewed every few years, on staying at the absolute edge of what physics allows. Get it right, and you're printing money at margins most industries can only dream of. Get it wrong, even slightly, and you're sitting on the most expensive empty building on the planet.